Okay, so good morning, good afternoon, and good evening. Welcome to the course series of Fundamentals of Integrated Sensing and Communications. So today is our final lecture and is lecture 8 given by Professor Yuanhao, and the topic is ISAC for low altitude wireless networks. So before Yuanhao presenting his talk, so I will have a brief introduction of Professor Cui. Currently, Yuanhao is an assistant professor with the School of Information Science and Engineering, Beijing University of Post Telecommunications. So he has been the founding chair of the IEEE Comsoc Spatial Interest Group on the low altitude wireless network, so the low-latency, and also the founding secretary of the IEEE Comsoc ISAC Emerging Technology Initiative. And Yuanhao also served on the editorial board for several IEEE journals and has organized several workshops, special sessions on ISAC in the flagship IEEE and ACM conferences. And he also received a lot of awards from the IEEE Comsoc conferences as well as journals. Okay, and moreover, I would like to advertise the first IEEE ISAC conference, so which is organized by IEEE Comsoc, IEEE Signal Processing Society, as well as the IEEE Aerospace and Electronic Systems Society. So this conference will be held next year, in next November, in Lisbon, Portugal. So you are welcome to submit your recent contributions on ISAC. And the submission deadline is June 1st. Also, we are also calling for spatial sessions and tutorials, and here are spatial session deadline and the tutorial proposal deadline both are on May the 4th. And also, I would like to remind of you, if you are interested in this lecture series, you can watch the playback on the ChatPad website. And thank you so much. So let's welcome Professor Cui to give his talk.
Okay, thank you. Thank you for the introduction. Let me show a slide. Okay, that's me. Yeah, hello everyone. Sorry for this actually because the video cannot change its location. So today I will give a talk about integrated sensing and communications and the low altitude wireless network. Basically, it's a present of our recent work in these two areas. So because today is, I think it's the final course for the integrated sensing and communication course, so I will go a little bit slow. And if there is any questions, please maybe you just can email me or or let me know. Yeah, let me start. So for integrated sensing and communications, we can see a lot of things. There is two driving forces for integrated sensing and communications. The first one is the technical trait. Because let's check back for the history. So we can see communication is changing from the military form and massive MIMO and for duplex. So in frequency and space and time domain, the communication is becoming narrowband and loss available. So basically, it needs more about beam management, and it needs to know more about the channel characteristics. So this is basically the radar task in the past few decades. They call it angel estimation and target tracking and Doppler estimation and time estimation, something like this. So from the signal processing phase, we can see communication is becoming radar. And from on the other side, let's check back for the architecture. And if we see the transceiver design in communication, we can see a lot of people are talking about machine learning, transceiver design, and for communication, we can see a lot of work on symmetric communication. So basically, in the processing pipeline, the channel estimation and information transmission is becoming together. So from this side, we can see the architecture also becoming radar, because when we talk about the channel estimation, it's basically the similar technology with radar tracking. And on the other side, when we talk about the deployment, now for the 5G and 6G communication system, the system become cell-free and become ultra-dense network. So we can see a lot of stations in the same area. So we in communication we call it heterogeneous architecture. So when many base stations located in the same area, we can get multiple access and multiple link from the user equipment to the base station. So it from radar side, it also can result in distributed radar deployment. So in a hotspot area, many radar and many sensing waveform can sense the target in the same area. So it can increase the range resolution and also Doppler resolution. So it will be the basic, it will be more interesting in the future. And from the other side, let's talk about radar. The radar is also become civilization usage because let's think back. For I think 20 years ago or 30 years ago, radar just used for military, and they used for tracking plane and also tracking ships and something like this. For now, many vehicles and many cars and also many planes they equipped with small radar. So when radar becomes small, they need a miniaturization, and also they need something to consider the general generalization, and also they need to think about the standardization because single process design and also their small equipments need to be standardization to cooperation. So now many cars, because many cars equipped with radar, we call it automotive radar. So radar people consider about the radar network and the radar interface management and also some standardization problem. So this is from radar technology, they are also becoming communication. So this is the main two technical trait for communication and radar. We can see communication is becoming radar and also radar is becoming communication. It's very interesting. So from other side, from commercial trade, because we can see a lot of commercial equipment such as Internet of Things device and phone and vehicles and smartphone device and also some smart city device. They equipped with same communication and sensing, and they both have communication ability and also sensing ability. So it's very it's very interesting to see if we can reuse the communication and communication hardware and sensing hardware together. Such as when we design communication and sensing hardware together, it will mean result in cost reduction, and also signal processing ability enhanced. And from other side, from frequency side, because we know many communication devices are using the frequency, and in civil, in traditional usage, radar may require small, or maybe they require some other bound different ways of communication. When we want to get into the such as vehicle, and they need to require and they need to approve some new frequency. So from this side, radar will also able to use communication frequency. So they can coexist with other device. They from this side, they can also reduce some regulation cost. And the final reducing is waveform, because in both communication waveform and radar waveform, they are electric waveform. So when we try to reuse this kind of waveform, we can reduce a lot of costs on waveform resource. This is the main commercial trait, because we can reduce a lot of costs in hardware, in frequency, and in waveform. It's very natural to consider about interface sensing and communication design. And when we say about the integrated sensing and communication, there are two kind of gains we may get. The first one is integration gain, as we talked before, and the third one is the cooperation gain. We will talk about it later. Because you can from the information processing side, if we consider sensing data, indeed, sensing data may also enhance communication ability. And there is a lot of work before, such as this. This is the work from I think it's Professor Health group, and decided when we tracking, when we co-located the communication transceiver with the radar could enhance the beam scan ability and also get faster beam alignment. Is very natural because the sensing data could get some prior information through communication. And the third one is we can also to construct a channel knowledge map for communication. If we know about the nearby structure, such as building and such as something else, we can naturally also we can infer some channel knowledge from the nearby structure. Also, it's very I think it's also a very hot topic in internet sensing and communications. The third one is communication assisted sensing. Because there are two sides of research you may consider. The first one is AD network. This is, I think, is old topic. Talking about the sensor network. If we don't consider the cellular network, such as because we have a lot of infrastructure in communication, we have a lot of base station nearby. It's a kind of infrastructure. If we don't think about that, sensor network have also lasted for about decades. They also used for military and used for, I think, Wi-Fi or something else. And the final one is we also could use communication network such as the current 5G or 6G network to assist the sensing. Then we can get a lot of interesting applications. I will talk about it later. So for the use case, let me talk about some kind of interesting use case. The first one is cellular network and vehicle network. For cellular network, if we integrate sensing and communications, we can get all weather day and night environmental monitoring capability. Because we have a lot of base station nearby. I think it's the world's largest sensor network as we can consider. I think it's something kind of plant level network. So the base station could also sense the humans and sense the vehicles and also to image some like UAV and also some humans to see because the resolution maybe also could be super could be get higher by some super resolution technology. We can talk about the scenario one by one. The first one is channel map construction. I think I talked about it before. And the third one is mobile crowd sensing. It can sense the crowded people nearby and also could localize and tracking them, and also could monitoring the UAVs, and also they could identify people by how they walk. And the final thing is they could get count humans and could localize and could cooperative localize and image something like vehicles. And for vehicle network, we could get a much higher capacity and also much better delay for this. There is some typical scenarios, maybe for the raw data exchange and also simultaneous localization and mapping, and also vehicle planting, and also it can get some extended sensors for the over the horizon sensing. I think this is a very interesting scenario maybe realized in the next few, I think 5 or 6 years. You will see that. So all in one, the future cellular network will become a multifunctional infrastructure with not only about communication, it may be with ability of sensing, also maybe it will be with ability of transportation. I will talk about it later. The third one is some capacity about remote sensing, because as we know, for communication, um, from we could estimate the path loss from the transmitter to receiver, because the path loss is exists everywhere, from the satellite to the ground user, also from the UAV to the ground user, also from ground user to ground user. Then we could estimate the channel. I think about the weather, and also about the rain, and also about insect. I show some picture here. This picture is construct how to construct the countrywide rainfall map. I think this is a paper published in National Academy of Science. They use the path loss of countrywide to construct a rainfall map for Norway and Finland. I think not the North European. And this one is about the inside section, because if we think about the insect, it can be sensed by the current base station frequency. I think it is about 3.5 gigahertz and 20 gigahertz. We can see them because currently there is a lot of insect radar deployed in many countryside. So if we could enable communication base station with this kind of ability, it will take place a lot of this kind of radar. It will be interesting in the future. The third use case, I think, is in the smart home, because we have every home has a Wi-Fi, and the Wi-Fi could sense in the surrounding environment by its channel state information. And there is a lot of typical scenarios. The first one is, I think, they can sense the human presence, and also they can sense how human moves, such as they could sense its proximate, and could sense human fall, such as, and also if it were near to your bed, it could also monitor your sleep, and also they could they could see some visual signals such as your heartbeat and also your breath. This is I will talk about it later, because we have also do some work on this area. So more interestingly, they could image people at this kind of resolution. You can see we can still not see how human look like, but we can just see a very blood human. So it's very interesting. We can see a lot of new applications in home by this kind of information is basically come from human activity and could be sensed by the channel state information. And we will see a lot of this application, I think, is out of the home. So let's go to the next stage, because we can see there is a lot of typical scenario can be used, also can be applied for intersensing application. Then a very natural question is, for current communication signal, which part can be used for sensing? And we have do some work on this area. The first one, we have also analyzed some LTE waveform and 5G waveform, because as you know, the very different thing between communication and radar is the communication always carries user data. From a generalized scenario and also general side, user data is always random. So communication is always transmitting a random data. I think a lot of people, such as Yifeng and Fan, had talked in last several calls. it will result in very difficult in in concurrent processing, because for radar, concurrent processing is important to increase its Doppler resolution. If we could not use it for concurrent processing, it may be very difficult to get a higher resolution for radar. Because communication is also narrowband. And for LTE, I think it's the maximum band is about 50 megahertz. And for 5G, I think the maximum band is about 200 megahertz. So for this kind of narrowband sensing, if we could not use the concurrent processing, the Doppler resolution, and also the range resolution is almost impossible to use for real application. So then in this case, the first thing we need to consider about is which part of current communication waveform is stable, which we think is for the reference signal. In this image, I have shown some kind of inference signal. The first one is position PRS, and the third one is CRS. This kind of reference signal is fixed in standardization, so everyone can get how it looks like. It will not carry about some random signal, so it's very natural to use for concurrent processing. So but another thing is how about its sensing ability? How about its range resolution and Doppler resolution? We have done some work on it. Its range resolution is I think is about 25 meters, and its Doppler resolution also very low. So for LTE, it looks like this. Then another thing is whether we could enhance or to modify its kind of structure. It could and can be done because in 5G waveform, even though its band is also very limited, but it can be. But this kind of signal structure and reference signal structure can be changed like this. I put the 5G NR frame on the left side. You can see the structure is a little bit different with the LTE signal. So, but more interestingly, this kind of structure can also be modified. But LTE signal cannot be modified. There is not this kind of ability defined in the standard. So if we could modify this kind of structure, we could get a different super resolution technology. Because in radar technology, we always use the stepped in waveform like this. And the waveform deployed like this, and then we could get some correct super resolution technology, and because of 5G provide this kind of choice, so we could deploy and also design some kind of stepped in waveform in 5G in the future to get super resolution to enhance its range resolution. I think it's a very interesting topic. And we have also done some experimental in the real world. So maybe we could publish it in later. And from another side, we have also done some beamforming design for ISAC beamform. So because we consider about a lot of low altitude network, and in this case, base station is always need to communicate with the UAV and also sense the UAV. So this because UAV is always a high dynamic target. So the channel maybe come from some error. We need to consider about some sensing ability, such as we need to maximize its sensing performance and also guarantee some kind of communication performance. This kind of work is motivated by this. In this work, we maximize its chromosomal band and also use out edge constraint for this. You can see this. Sorry. And this is another work. we use MSE as a minimization to enhance its sensing capability, and also bounded by the SNR of edge capability. So this two work is a similar. We track this kind of problem by as SDP relaxation, and also use some math technology to solve the problem, such as I think we write it here by Bostonian inequality. And the next slide of work we have done is about energy efficiency and ISAC beamforming design. Because energy problem for communication is always an important problem, and also its mass structure is quite different with the radar. We can see the mass structure is like this. When there are always and we also measure it by this is a channel capacity, and also to bounded by some kind of sensing energy efficiency. And the most important thing we have done when trying to do this search is how we define the sensing energy efficiency. And finally, we decide to use the kernel bound to its I think it's power. So this problem is a kind of dual objective Pareto optimization problem. So also we tracked it by using a lot of math technology. This is another side of our work. The next thing is when we consider about the stage of cellular network, we need to qualify how it senses and how we provide a sensing service to the user. It's because we have a lot of constraints and a lot of performance, and also a lot of things can be measured from sensing side, such as we can use the detection probability, and also we can use the tracking accuracy, and maybe we can use the voice call rate, and also maybe use the video transmission rate to measure the user service, the quality of user service. But for sensing, we currently still not have this kind of universal and also well recognized service qualification. I think to talk about this. So when we're trying to provide the sensing service to users, we need to define how it should look like. Such as when the detection probability lower than something else, we need to stop its bill. We need to increase the user bill to get more detection, to get a higher detection probability, and also for localization and for tracking, it may be measured by different constraints. So in this work, we have provided a lot of sensing performance measurement technology. This work is published, I think, firstly in IEEE network and secondly in the IEEE TWC. And I think we provide some communication constraints and also the physical resource constraints and also fairness constraints to qualify the sensing service. And also we provide some theoretical limiting constraints and also some inequality. All this is a different side of convex problem. You can see we can get a lot of trade-off in this image. You can, such as in this image, we can see a very natural trade-off between the MSE target and the MSE for the ISAC target, because when it increases another side, when the communication performance increase, always the sensing performance decrease. It's very natural because we should allocate more resource to the sensing for communication. And the next thing is for communication waveform design, the near field and the far field design is quite different because we are trying to use base station to track human activity. So in this scenario, the human always localized very near to the base station. So I think it's very hard to say model. We could model them as a far field target or far field user. In scenario, the channel is very different. Also, the target is very different. So from communication side, it's an interesting problem. Because in the far field, you can see this image. In the far field, the communication always looks like very straight forward. And for the near field, we should do firstly beam focusing on the beam, and then to localize its localization. So there is a significant overhead of beam training and beam focusing. If we consider about this kind of beam training and beam focusing, we need to use a lot of more technology to reduce this kind of overhead. In this work, we try to use some reinforcement learning technology to firstly localize the people by sensing, and the thirdly to put beam on their location. Okay, so I think this is what have done in ISAC reform. And the next thing is we need to talk about the ISAC data, because I think one of the most important thing in this scenario is we always have not enough uh, uh, sensing data, especially wireless sensing data, to encourage people to use machine learning algorithm or some data-driven algorithm to track real problem. So if we look back for the video or for image recognition problem, they always have a lot of data. So why don't we construct a very large data set to encourage the wireless sensing scenario to go forward? This is what we are trying to solve. Uh, when we, but however, when we look back, we can see there is very few data set for ISAC, and the size is very small. I think the difficulty here is because the sensing data, especially radio sensing data, is very hard to label, and also they very hard to collect because for an image we can everyone can recognize the image, but not everyone could recognize, even for myself, to recognize a radio signature. It's very hard to label, so the data is very few. That's why we try to construct a very large insight for this, and also we are doing this. Today I think we have constructed about 40 data set for the ISAC. When we're trying to construct this kind of data set, one of the things is how could we make the data set generalization? Because the sensors is very different for wireless sensing. We have base station, we have Wi-Fi, also we have phone, or also we have some such as SDR, a lot of different radio sensing technology, and also a very different radio sensing hardware. And because we always want to encourage everyone to design a generalized algorithm for all these devices. So the important thing is how could we design a general enough data set. So basically, today we are trying to use the LiDAR and radar in 60 gigahertz and 77 gigahertz, and also some 3.5 G data database station, and also I think we have 20 G Digital Health Base Station, and we have a different kind of Wi-Fi from Huawei, from ZTE, and from something else, from some company else. So we are trying to use this kind of hardware to connect a lot of different human activities in different scenarios. I think we have in this work we have collect 4 scenarios, but we're trying to collect I think the design is about 15 scenarios in the future. And also we have about 600 volunteers here in BUPG, and they are all willing to get involved in this data collection experimental. And so I think it will be a very large design in the future. We will publish it in the it may be I think half year later. And and another thing is we are trying to design a sensing data sharing platform to support data sharing. So this platform is initiated by ISAC ETI and co-developed by Huawei and a lot of academic industries. And today we have more than this is 4 TB data, and also we have around 30 I think we have about 40K minutes data, and we have approaching 100 I have approaching 12K data samples. So this is our SDP platform currently look like. So we are also encourage everyone to get involved in it and also submit your work data here to get more support and to contribute to the community. And the for to support this SDP data platform, we also construct a mobile SDP sensing challenge in mobile COM 2025. It just finished in last month, I think, in Hong Kong. So we have about over 300 teams involved, and also 1,000 participation here and there. And also we also get a lot of these sponsors in such as Huawei, Intel, Gaotong, and LG and ZTE. They are also major players in the field. By the way, we may have another certain challenge in the future. And from our side, our team also have designed a sensing data sharing protocol and trying to benchmarking and trying to contribute to this kind of world sensing task. Because we know that the data always from different hardwares, but we could construct and reshape it to a tensor. This tensor is maybe you can look like here. This tensor is a 3-dimension or 4-dimension tensor, and when we could reshape it to a unified tensor data structure, we could use a lot of learning technology to recognize it and to do a lot of processing in the future. It will be benefit for the communication and also for the computer science people, because not everyone could modify the physical layer side, and not everyone could modify its I think its data collection setting. If they could get unified data in the future, I think there is a lot of algorithm could come out from different researchers. So this is what kind of work we have done currently. We are doing currently. So the next thing is an interesting topic we are doing. we are doing a Bruxism recognition because as we know, everyone, not everyone, but I think 40% of current humans they always have a Bruxism Bruxism when they are asleep. So when they feel it's very hard for your teeth, you always go to hospital and always it will be very late. It is very late. So if we could recognize this kind of bruxism in very early stage, it will be very good. It will be good for a lot of people to do a early check, and it will be good for your teeth and for your also for your money. So this is what we're trying to do. We're trying to use radar waveform to recognize this bruxism in when they sleep. So the problem here is because this kind of bruxism movement is very small compared to human activity such as falling and walking and also wave hand. It's this kind of Doppler signature is very small, so it always be overwhelmed by the breath and also by the heartbeat. So the problem here is how we could extract this kind of signature from very strong background noise. We are trying to do this, and also we get looks like a good result. So this work we have submitted to ISAC in 2026, and we will do this. I think this is the big topic. I think we will do this for next year. And the next thing is we are trying to do some edge perception work because when we think about the real the how because when we think about how we deploy intersensing and communication in the real world, it always be in the base station or in your phone. Basically, we think it will be better in the base station because base station is a better and stronger computation unit compared to the phone. So edge perception will be a future. So when we talk about when we considering sensing in the base station, we need to think about how the sensing data could change the current network structure and also change the network data flow. We think there will be a specially designed protocol in the future to also to calculate and to pre-process the sensing data in the BBU, and also there will be a lot of early I think early recognition algorithms and applications deployed in the base station. So that's why we think there will be a different network structure. We call it as edge perception. And the next thing is for edge perception, what's different maybe? Because when we consider about the different structure and a lot of sensors trying to sense the same scenario as we see in this image, such as when we have K device trying to sense the same scenario, there will be a lot of I think there will be I think there will be the spatial component will be very strong. So we could pre-process the data collected because there may be a lot of unnecessary information, and we could pre-process it at the network edge. And when we get a very small or something and a very important sensing data, we can transmit it to the edge server and also transmit it to the cloud to get better computation. So this is what we're trying to do. In this work, this work is submitted and accepted by the Trans on Wireless Commission, and we have done some over-the-air aggregation and to get better data transmission and to reduce its data to reduce its calculation overhead and get better training and higher accuracy. This is a training curve, and we can see the training and the testing accuracy is very high, and also. And the next topic, we are going to low altitude network. Sorry, low altitude network. As we have said, we think the most important application scenario, except the in-home wireless sensing, the most important scenario in the future is low altitude wireless network. A lot of people have asked me what's different with the low altitude wireless network between the low altitude network with the UAV communication. I think it's a kind of different structure because low altitude network, when we talk about low altitude network, we are trying to see from the side of the base station. We are trying to construct a ground-based network to serve UAV and also to serve some flying vehicles and except UAV. So it's very different with UAV because we have charged a lot of UAV work in the past, I think 3 months. A lot of UAV trying to design its trajectory and also trying to serve ground users from the, I think, low altitude airspace. But this is different with what we are considering about. In the future, the cellular network and also the base station will serve as the air traffic infrastructure. So the most important thing is we try how could we use the base station to manage the air traffic, not only about the one UAV, it will also not only about one UAV's communication, it will serve a lot of UAVs. I think it's millions or something else. So in this consideration, the structure is very different because we need to consider about a lot of different scenarios such as the regional monitoring areas such as airway and also air corridor, and also to construct a different flying space. So this is the important thing. Not only about the communication, there is a lot of things to sense the UAV's altitude and the UAV's position and how UAV flies. For low altitude wireless network itself, it will be a 3D network from 0 to 3,000 meters in the low altitude airspace. It will be serve communication and serve sensing and serve and provide some kind of calculation service. More importantly, as I said, it will be served as an air traffic infrastructure rather than for only communication. So we have an image to see how this network looks like. Also, always we will have a GNSS satellite, and also we will have large UAV and large flight. But when we talk about the altitude higher than 3,000 meters, and the base station could not able to serve them because it's so high and the signal power is very small. So we're trying to discuss is about the below 3,000 meters. There is a lot of things, different kind of UAVs, and also there is also some kind of ground base stations, and also there will be some restricted field, and we will talk about it later. So when we think about the low altitude wireless network, what will be served? What it will be served? There will be a lot of different UAVs such as multi-rotor UAVs and also unmanned helicopter and fixed wing UAV. They are in different altitude. And also, we think the most importantly is eVTOL because in the future eVTOL will be a large service. We can see a lot of them in Shenzhen, but we will see them in the future in worldwide. So for application scenario, there will be will have shown some kind of application scenarios such as agriculture and low altitude logistics, and also UAM, and this is called uh, urban air mobility, and also there is some environmental monitoring service. So for all this kind of terminals, they always equipped with some kind of sensing type, such as vision and GPS, and also some always the equipped with they equip a lot of them, different kind of sensing service. And also they need base station to provide actual sensing service for them, because they could not always they could not aware the environment very sensitive, because the flight, especially the UAV, is always very not very fast, but it's very how to say, it may be very some dangerous, because when we try to drive a car, and people could always when there is a car accident, people may be injured, but maybe not hard. But when a UAV fall from your hand, it will always cause a lot of damages to the not only the humans, but also the some other application, some other stuffs. And the next thing is how it will look like when we talk the low altitude wireless network will serve the airspace as air traffic infrastructure. Let me just give some example. The first example is how it will look like in the future when a UAV flying. I show the different airway altitude, because UAV there is no man in UAV, so it of course could not look like the taxi or cars on the ground, because they could, when there is a human, the human itself could decide by itself. But the UAV is controlled by a remote human, or controlled by a computer software. So we should design is how it's flying, and also how its available space looks like. In the future, I think in China at least, the airway will be only one, will be possibly only one side. We could look at this image on top of this, the helicopter here, also we could say it's eVTOL. The eVTOL here, it could only fly from the right to the left, because this is a one-way entrance, and below it, there will the helicopter will fly from left to the side to the right. This is always also a one-way entrance. So when we construct this kind of airway, we should monitor how the UAVs in it behave. Because when the UAV exceed or suddenly get very high to the next station, to the next airway, or to the different airway, it will be caused, an accident will be caused. Basically the minimum distance between these kind of airways is about 100 to 200 meters, and the vertical altitude of it will be larger than 60 meters. Also, this number is not very precise. It may be changed in the future, because when we could monitor it more accurately, we could get more traffic in the airspace. So the another important thing is how could we construct this kind of airway? We could provide more sensing ability, because we should provide a continuous sensing to the UAV. Not only itself, we should monitor all the UAVs on the ground, because if there some of them could monitor and some of them could not, it always it also could cause some kind of accident. And also we may use different kind of sensing data, maybe use radar and lidar and for radio to monitor it. So we should do some multimodal fusion in the base station, and also we should able to detect and sense very dynamic target. And also we should, more importantly, we should do real-time communication because communication because the communication link from the UAV to the ground is a control link. The control link could not be interrupted. It should be high reliable and also maybe should be high capacity. And for airspace management and flight construction, it will be different. In the last PPT, in the last slide, I just show how the technical scenario looks like. In this slide, I will show how the airway contract will be done. In this image is what we have published in the I think in September. So you can see the airway in the future may be very complex because there may be some flight above 3,000 kilometers, and between 300 to 3,000 kilometers, there will be different kind of airway. There is because this is 3D scenario, the flight may be from up to down and from right to side, something like this. So to construct this kind of flight and guarantee its efficiency is also very important. Also in some specific area, such as some important area, it should be the UAV should not enter them. When you're trying to get in it should get something like a warning and to force to land down. So so this kind of airspace structure is what we should to image in the future. So how to construct it? We have a lot of methods, such as we could use 5G base station, and we could use ADS station, and also we usually use some satellite station to use them. In this image, we will show how it will be constructed very efficiently in it. And this is the performance we have. This is the performance we have proposed from our work. So maybe if you are interested in it, you could please check this work here. And the next typical scenario is for the low altitude wireless network is the critical landing down state of the traditional helicopter. Sorry, the traditional plane, because this image is a hand-write image by myself. So we could just to give example how it looks like when a plane trying to take off and landing down. The first thing is when a plane trying to take off, it will be take about 3 meters. Sorry, it's not about 3 minutes. It's about 10 minutes to take off. Firstly, it should the crew will call and they will close the door of the plane, and then they will off the blocks and they will take off and to power its engine. After that, it will fly. It will fly very repeatedly. I think it's in 3 minutes. And after some kind of flight, maybe a very long flight, when we get to the destination airport, it will be landing down. For landing down, it will be also take about I think 10 minutes. For in total, we call it a black 10 minutes because a lot of accident happens in this in this stage. For all this takeoff and landing down stage, we should estimate the altitude of this airplane. Not only about its location, we should be aware of its altitude, because if it's not correctly get into the airway, which is precise, it may cause some kind of different it will possibly cause accident, because when a plane get landing down, there is a lot of high buildings around. So if its altitude different, it may be cause some crash. Currently, for the airport, there is some kind of different landing down device. The first one is, I think, is in most of the airplane, is by the it's the approaching of the airplane is done by the eye of the driver. It's very interesting, because capital it always could see the airplane, and they could use some kind of driving skill to control the altitude of the plane and landing down. And this is the most common scenario. And the next one is there will be when our airplane is very high tech, there will be some such kind of guiding device, such as a radar in the airplane, to estimate the approaching of and see the approaching of the airplane. So using this kind of signal, they could get the location of the airport and the destination and the height of the current stage, but always they will not get its own altitude, because the plane is very huge, and also it will be always a large airplane. So there of course will be some sensors on the plane, but it's not a very current. So the important thing is, how could we estimate and get the altitude of the airplane when it's trying to landing down, and also when it's trying to take off? This is the important thing. Let's take an example. This is the airport in Taipei, I think. When a plane trying to get landing down, they will go to this gray block from left to the right, and between this stage there are two stages. The first one is initial approaching. It will start from 30 kilometers away from the airport. The altitude will always to 1,000 meters, and this stage will last, I think, 10 kilometers, and they will get into the middle approach. For middle approach, the altitude will be 200 meters, and it will start from 20 kilometers away. And for the final stage, it will be started 10 kilometers away, and the altitude will be 300, which will within the airport area. So, but for radar, for the radar in the airport, it will be always not necessarily very the coverage of the radar will not be lasted so long, which means we could use the base station around the airport to estimate the altitude of the plane. This is a very interesting topic, because we are trying to do some because I think for airplane, they are currently they not cooperate with collaborators, I think. So this is an important topic. I think this is some important scenario. And what we have done in this topic is we call it predicting beamforming, because for airplane, in this image, we just use vehicle on the ground to show this case, because this basically we could track the target and to estimate how it's moving and to get a trajectory. So for a base station, we could always to estimate a high-speed vehicle and also maybe a high-speed airplane and maybe a high-speed UAV to get its location and then to localize the beam to the target. So it can be used to estimate the airplane's altitude and to estimate the airplane's approaching. This is an interesting topic. We have done I think this work is using base station only and trying to use the wireless sensing data to support to estimate the target, where the target look like, and then try to remove the beam management and the beam alignment stage. And in this topic, and in this work, we try to use vision signal and radar signal and lidar signal and positioning data to estimate a target movement, and then try to remove the beam, try to remove the beam alignment. And this kind of predictive informing could be naturally used for the scenario I mentioned before, because it's very because when we're able to track a moving target, we could always get, for example, image for it. We could also to predict how it look like. So then the base station around the airplane will support the radar in the airport. It's a very interesting topic. And then in the third topic, which is similar, we try to use cross tension mechanism to increase its to get some, I think, some high accuracy. You can see the accuracy is almost 100%. Okay, let's go back. Then the topic scenario 4 is large scale UAV, because when we talk about the low altitude network, we are trying to solve a number of UAVs in the future. One UAV may be not, because we could always see some UAV flying in the airplane, flying in the airspace, but in the future there will be more. So when UAV become more and more, it will be very different with the traditional UAV on the ground, because when a man holding a phone going around, or when a vehicle going from this road to another road, the trajectory is predictable, and also their channel is very, I think it's also predictable. So for terminal like UAV, it's different with the terminal on the ground. The shadowing and the information shadowing and the communication frame design is important in the topic. So also from something else, from another side, when we considering about UAV fly procedure, because UAV always try to take off and landing firstly, they should firstly take off, and when they fly in the airspace, they should do something like network registration and airspace authorization. Then they able to get into the airway or air corridor. So when they get into air corridor, they should establish a very strong and reliable control link to make the flight stable. And also when they should have some collaborative mechanism to avoid accident, to avoid collision. And finally, when they get the destination, they should landing down. So this is the whole flying stage. In this stage, they should connect to the cellular network multiple times. So this kind of interaction should be defined in our future standardization, and also we should also I think we should also cooperate with traffic department to do this kind of things. Okay, the final topic is about UAV capture. When we trying to do some UAV research, an important thing is how could we when flying UAV is illegal, how could we stop them? There is a lot of method can do. The first thing is we could do some kind of interference. Also, we could use some laser weapons to destroy it. Also, we could use missiles to destroy it. But I think it's very expensive. The more I think more reliable thing is we could use UAV to capture the UAV. So it will be look like a ISAC hunting procedure. But in this problem, the different thing is the airspace, especially for the city airspace, is very complex. So because there is a lot of buildings, there is a lot of some flying things around. So when we're trying to capture this kind of UAV, such as using a net, and we should firstly try to pursue it. This is a kind of we call it a pursuit evasion collaboration. So in this topic, we have do some interesting work. The first thing is we try to use a decision network to capture it. You can see the decision file here. This is the Hunter. This is Hunter 1, Hunter 2. This is the Hunter 3. This is an illegal flight. Then when it goes to here, they capture here. The currency also, I think the currency also is about nearly 19%. The next work here is we try to do this procedure under channel error and also under communication error, because the communication link is sometimes unstable, and also in this stage they may not get the get all the information they required. So when they missed some important information, whether they could capture this kind of illegal flight, the illegal UAV, it's an interesting topic. So the result here is you can see it's a little bit down. The success rate is about 80%. And the third thing is we're trying to use because maybe not every hunter is use same UAV. They maybe have different kind of UAV, so the UAVs is maybe with different capability. In this case, we developed a graph reinforcement learning strategy to give each UAV different weight to characterize its power. Because some of UAVs may be very powerful, they with very high speed and very high intelligence, so they could capture it very fast, and some or not. In this case, we can see the success rate down to 60%. I think because the scenario is very complex in the setting. For this three work we submit to IEEE Trust Mobile Computing and TCCN and LTG. So the final thing here for the topic is I will try to summarize some kind of new topics in the low altitude network. The first and the different challenges. The first thing is for communication. For communication, we need to design a 3D coverage network, because current base stations they are designed to serve on the ground users. So when you're trying to serve UAVs, especially a number of UAVs in the airspace, and the network structure may be changed very different. Also, when the base station try to 3D scenario, there will be a lot of survey, a lot of airspace maybe not able to survey. So it's also it may be a different thing in the future. And the third thing is the air and ground capacity is very imbalanced because when we're trying to see the path loss for the air link and the ground link, you can see because there is a lot of reflections on the ground. So the signal will not cover a lot of areas than ideal space. But for the air current, the current in the airspace it should be larger than expected on the ground. So it may cause some kind of interference problem and some kind of handover problem in the future network. And the third one is how could we cooperate between the ADS-B and cellular network, because currently the air the air traffic department they use ADS-B as the basic communication standard. So in this case, we should always do some cooperation around them. And the third one is when UAV across different cells, they may cause cross-cell interference, or we could call inter-cell interference formally. And in some kind of stage, when a UAV flying very fast, the handover between different base stations is also a big problem. Especially, it looks like when a train going very fast and across a lot of base stations, and you can see the signal is very low, and so they will do a lot of retransmission to fix the problem. But for UAV, it's not possible because they should have a very reliable controlling. Otherwise, they may cause some kind of crash. And the next one is how could we identify UAV in using wireless sensing technology. And the next one is how could we force UAV down only using wireless signals. This is a very important problem for communication side. And for sensing side, there is also some challenge. The first one is because most of UAVs they are low, small, and slow target. And how could we use narrowband sensing because the current base station, the maximum bound, I think not exceed 200 megahertz. Using this kind of narrowband, we could not estimate and we could not recognize the kind of UAV. So some kind of super resolution technology should be deployed here. Then, sorry, this is this one is different. And the next one is how could we construct a high precision 3D air map? Because the map for the airspace is different ways the map for on the ground. Because the building and also the road maybe not changed every time, but the air condition and also the some kind of different wind may become, and also I think the structure may be changed very fast for the air condition. I think the next one is positioning for the aircraft. 就是when we trying to position UAV in a 3D airspace, how could we get its exact position and localization? It will be very important because it's a 3D space and there is a lot of interference there. And also we should also do some sensing data fusion for multimodal data. And the final one is for the air traffic control, because nowadays for the air traffic, they use very old style control technology, which will mean one flight, which means when you're trying to fly, you need to get approval physically. So we should digitalize the airspace, and when we try to digitalize the airspace, the base station will be a key point here because it's the most important infrastructure on the ground. We may not able to deploy a new infrastructure, especially for airspace traffic. So when we try, so in this case, we reuse the base station for airspace traffic control will be very natural. And the next one is, as I would say, the airway construction and management is important topic. And the next thing is, I think, the collision prediction and avoidance. This is also an important part of air traffic control. And theoretically, the trade-off between the airspace capacity and the communication capacity is an important topic because when a base station trying to serve different UAVs, they should allocate different resources to them. However, this kind of resource may be conflict with the communication side, especially this may be a wireless resource. So there should be a trade-off between airspace and communication capacity. This is I think we are doing topic in this several months. And the final one is electronic fence construction. So, okay, so this is my talk today. And thanks everyone for your time.
Yeah, thanks Yuanhao for the nice presentation, and I have received a few questions. Okay, so first question, and I see one of your slide mentions joint transformation. So one audience is asking, so as for communications, the channel is impairment, and we want to perform equalization to recover the data. But for the radar, the channel is the data we want to keep. So these are actually opposed mathematical goals. So how can you do this within a single unified processing pipeline?
It's a very important question. In current, I have saw some kind of machine learning work. They trying to do them jointly, but mathematically they are different. They are of course different target. So for math, for math, from math aspect, we also think one of them is deterministic and trying to estimate another. And if also we have some work have done to join estimate, but the accuracy I think is not very high. But for learning, it's a different topic. So learning for data-driven method, there may be a lot of not a lot of there may be some work I have talked about later, but the accuracy may be not very high. This is just the target.
Yeah. Okay. So the second question is regarding the air computing. And actually, the air computing involves some analog noise. And over many training runs, will this noise accumulate and prevent the model from converging? Yeah, it's a convergence issue. Yeah.
Yeah, it will, I think, but also it's a nice question. Yeah, it will influence the occurrence. And we have done some work, but I think you can check this work. Maybe get some.
Yeah. Okay. So yeah, maybe you can check this paper. And the final question I believe is regarding the low altitude wireless networks. So in the low, there are various vehicles and using different communication protocols as shown here, right? Some are using the ADSB and some are using the 50 advanced and also satellite. So how can this kind of HLWN handle the latency caused by the translation and handshaking between different protocols? because we consider
That's a nice question because in this work we didn't consider this kind of different communication protocol. We just assume they could be controlled by this problem have been done in this work because this work is trying to define the air calendar design, not about the communication design. But I think you mentioned the problem you mentioned is very, very important. We're trying to do it in the future.
Okay, so maybe could you comment that we need a unified and a brand new standard for the low altitude communication? Maybe you can, just make some comment.
Yeah, maybe we need, but I don't think we could, because for different communication protocol, they have different companies are using them. So we could, of course, we could design a unified protocol for all of them, which is Stage G trying to do. But the future, I'm not sure it can be done.
Okay, yeah. So I think that's all questions. And thank you, Yuanhao, for this presentation. And
Okay.
again, so I would like to remind all audience that the playbacks can be you can watch them on the ChessPack website. And thank you for attending today's talk. And thank you so much. Thank you, Yuanhao.
Okay, thank you. Thank you.